Welcome to this explainer. Look, what if I told you that you could assemble a completely local C#-based AI inference engine and actually get a streaming reply from a large language model in just about 30 seconds? Seriously, 30 seconds. No complicated Python environments to wrestle with, no bloated dependencies, just pure native performance running right there on your own machine. Today, we're diving into TensorSharp. It's this brilliant C# inference engine specifically designed for running language models locally using GGUF files. It's incredibly efficient, natively compiled, and we're going to walk through the exact steps to get it set up on your rig. So, the big question we're tackling right now is, how fast can you actually run local AI? A lot of times setting up local LLMs feels like trying to navigate this massive maze of conflicting libraries and huge installations. It's frustrating. But for this explainer, I want you to think of TensorSharp using an engine metaphor. We are completely bypassing all those bloated environments. Instead, we're going to assemble a clean, super efficient, highly optimized local AI engine, piece by piece, directly on your own hardware. To pull this off, we've got an exact 4-step roadmap to take you from a totally empty folder on your computer to a running, intelligent local interface. We'll lay the foundation with our prerequisites, move into construction by cloning and building, pour in the fuel by downloading our model, and finally, ignition, firing the whole thing up. Let's get right into it.
All right, starting with step 1, the foundation.
Now, obviously, before you can build a high-performance engine, you need the right tools in your garage. And the good news? These core prerequisites are incredibly accessible. You don't need some massive, expensive suite of enterprise tools. Really, you just need the .NET 10 SDK, Git for version control, and, basic network access so you can actually download the source code and the models. That's the core of it right there. But if you really want to tap into the raw horsepower of your machine, you'll definitely want to look into the optional GPU tool chains.
And this is where your path kind of diverges depending on your hardware. If you're running a Windows or a Linux machine with an NVIDIA GPU, you'll want to install the CUDA Toolkit 12.x. That's going to let you take full advantage of direct GPU acceleration. On the flip side, if you're rocking a Mac with Apple Silicon, it is remarkably frictionless. You literally just need the Xcode command line tools because Apple's Metal API is already baked right in. And the best part is that TensorSharp is engineered to leverage both of these perfectly.
Okay, moving right along to step 2, construction.
With our foundation locked in, it's time to actually assemble the TensorSharp engine from the source code. And I promise you, this process is incredibly straightforward. First, you just clone the TensorSharp repository using Git. Second, you run the standard .NET build command. That's it. Now here is where TensorSharp does something truly wonderful behind the scenes. The native GGML library, which, by the way, is the C++ backbone doing all the heavy computational lifting, it automatically compiles itself on the very first build. Yeah, no manually wrestling with separate C++ build scripts unless you actually want to. The framework just handles that native bridge entirely for you.
Which brings us to step 3, the fuel.
So an engine really can't do much without fuel, right? And for TensorSharp, that fuel is the GGUF model file. If you're not totally familiar with them, GGUF files are basically quantized language models. Quantization is just a clever technique that compresses these massive AI models so they can actually run efficiently on standard local hardware, without needing hundreds of gigabytes of RAM. When you go to download a model, you're going to see different quantization levels. Like you might pick a Q8_0 file if you're looking for higher quality generation, or maybe a Q4_K_M file if you're dealing with tighter memory constraints and needed to fit a smaller RAM footprint. The really cool thing here is that TensorSharp can perform native matrix multiplication directly on these quantized formats. You don't have to waste time decompressing them into heavy 32-bit floats first.
So what should you actually download first? Well, the TensorSharp test matrix explicitly covers a few highly recommended verified starting points. You've got QN 3.5 and Mistral 3, which are both absolutely fantastic. But if I had to make a recommendation, I'd say start with the Gemma 4 E4B model. It's a relatively small, super well-tested option that you can download pretty quickly. Plus, and this is huge, notice that Gemma 4 supports incredible multimodal inputs. That means you can eventually feed it images, video, and audio, and have it all processed completely locally by your new TensorSharp engine.
And finally, we arrive at step 4, ignition.
All right, now that we've got our C# engine built and our GGUF fuel downloaded, it's time to actually run the application. To do that, you just need to tell it which transmission to use for your specific hardware setup. We call this the backend. It's super easy. You just pass a flag when you run the app. So if you're on a Mac with Apple Silicon, you'll use the flag --backend ggml_metal.
On Windows or Linux with an NVIDIA card, just use --backend ggml_CUDA. And hey, if you don't have a GPU or maybe you just want pure portability for debugging, you can simply use --backend CPU. It's literally that simple to perfectly map the software directly to your hardware strengths.
Now, I really want to pause and highlight this quote straight from their documentation. Every backend falls back to CPU for any op it does not yet implement. Guys, this is a brilliant fail-safe mechanism. It essentially means that even if a specific weird mathematical operation isn't fully supported by your specific GPU driver yet, the engine is not going to crash on you. Nope, it just seamlessly hands that specific task back over to your CPU. That ensures your AI's output is always correct and completely stable, regardless of what hardware limitations you might be bumping into.
Okay, so the engine is running, but how do you actually interact with it? Well, TensorSharp gives you two primary ways to take it for a spin. You can boot up the CLI, which is this raw, terminal-based read-eval print loop. It's absolutely perfect for debugging, running synthetic benchmarks, or if you just want to chat right there in your console. But if you want something a bit more visual, you can launch the server. That gives you a rich, web-based chatbot UI right in your browser, complete with file uploads and message editing. And it gets better. It actually spins up HTTP APIs that are fully compatible with Allama and OpenAI. Think about what that means. You can literally drop TensorSharp right into any existing AI tooling you already use, and it'll just pretend to be an OpenAI server, except it's running entirely locally right there on your desk.
So let's recap. In just 4 quick steps, grabbing the prerequisites, building the source, downloading some GGUF fuel, and picking your backend, you have gone from zero to a fully functional, highly optimized local AI engine. You've total privacy, complete control, and blazing fast inference. So the only question left to answer as we wrap up this explainer is, what are you going to build first with your perfectly configured local AI engine? Honestly, when you no longer have to rely on cloud APIs or constantly pay per token or sacrifice your users' privacy, how does that fundamentally change the software you're willing to create? Go grab the code and start pushing the limits of your own hardware today.